Hi guys, I'm going to be going over problem 35 from week 9. And for this problem we want to describe the cycle for a heat engine. And it's broken down into 7 steps. And just to quickly go over them, in the first step we have this piston that gets locked, so it's going to be isochoric with a constant volume, and we are set at 1 atm and 50 centimeters cubed. In the second step, we add heat to this system and our pressure will increase, and we get our first part for the cycle. It's a vertical line going up with constant volume, and we have an increase in pressure, and we're going to label this part of the process A. Secondly, we remove the pin and we have an expansion. This expansion happens at constant pressure, so we get this horizontal line, and we will be labeling this B. After that, here we will reinsert the pin, so we're going to have a constant volume once again. This will now be isochoric, and we are going to be cooling it, so we will have a decrease in temperature and also a decrease in pressure. So we'll get this curve here, which we'll be labeling C. For step 6, we remove the pin, so since the pressure had been lowered down and the temperature had to go down, the piston is going to compress, and we're going to have a decrease in temperature, so we have this low horizontal line going into the negative direction. And then finally we arrive back at our starting point. So our final PV diagram for the cycle of this heat engine will look something like this, where it starts at this point and it goes all the way around through process A, B, C, and D. Now for part B, we want to find the work. So to find work, it's simply the area enclosed by our four curves. And since this process is clockwise, since it's a heat engine, our work is going to be positive. And like I said, the work is just simply our area. So we want to find the change in pressure times the change in volume. So our change in pressure, we have our final pressure, which is 3 atm, minus our initial, which is 1 atm. So we have 2 atms, converting that to pascals. So our change in pressure is going to be 2 times 10 to the positive 5 pascals. Similarly, we find the difference in volume. We have 100 centimeters cubed minus 50 centimeters cubed is equal to the 50 centimeters cubed. And so converting that to meters, our change in volume is 50 times 10 to the negative 6. We simply multiply our change in pressure and our change of volume, and we get that the work done or produced by the heat engine is 10 joules. Now for part C, we want to find the thermal efficiency, and we know that for a heat engine, the thermal efficiency is the work out divided by the heat in. And from part B, we found out that work out is 10 joules, so we don't have to do anything for that, but we do need to solve for the denominator here. And dN is the heat produced by process A and process B here. So in this chart, only A and B will produce heat, since here we have a pressure increase, and here we have a increase in temperature, so we have a volume increase. Whenever we have a compression, for these we will have heat escaping the system, and we only want to calculate whatever is coming in, so it's only A and B. So for the first process, we have A being constant volume, so we use QA equals to NCV delta TA, and CV is 5/2 times R. We simply substitute that in, and using the ideal gas law, we arrive at the conclusion that QA is equal to 5 over 2 delta PA times V. Now we plug in our change in pressure, which is a 2 times 10 time to the 5th power pascals, and the volume for process A, which is at 50 times 10 to the negative 6 meters, and the total Q for A is 25 joules. We do pretty much the same thing for part B. Only difference at this point we have a constant pressure, so CP is equal to 7 over 2R. Similarly, we use the ideal gas law, and we have this conclusion here. We plug in our known values, and we know that QB is equal to 52.5 joules. So now the total Qin is 25 plus 52.5 equals to 77.5 joules. And finally, our thermal efficiency is simply the 10 joules divided by the 77.5, and this is equal to 0.13 or 13%.